Our diagram for this question shows what appears to be a cart moving to the right. It collides with this other cart that seems to have this compressed spring inside it. And after the collision, we see that the two carts are moving, and there's a question mark around the arrow, meaning we don't really know what the direction or the velocity or the speed is. In other words, we don't know what the velocities are after the collision. But we can see that this spring has unleashed itself, it's released itself. So at once we have a collision, and we also have an explosion. Remember, if we have two carts that are together like so, and there's a spring in the middle and they explode, they will move off. Now, what we know when an explosion happens is that momentum is conserved, and that's because this positive momentum is equal and opposite to that negative momentum. But what we know is that the initial kinetic energy is zero, but afterward there is a lot of kinetic energy. And the reason for that is energy is added to the system. Now, the explosion could be a chemical explosion, so chemical energy is converted into the kinetic energy of the motion of the carts, or it could be a spring where there was stored energy inside the spring releases that energy. But what we expect when there's an explosion is that there is more kinetic energy than what we started with. So we can be guaranteed in this situation both an explosion and a collision will have conservation of momentum. But what we should expect to happen is that there is more kinetic energy than you would expect afterward. So let's read the question, and we find that they have the same mass. Very important information. So this mass equals this mass equals this mass. Negligible mass on the wheels travels to the right, which is initially at rest. So we know this V0 equals 0. The spring-loaded plunger, stored energy, pops out, staying in contact with the cart for 0.1 seconds. Negligible mechanical energy dissipates during the collision. So what we're saying is that the kinetic energy is not lost due to the collision. So according to this, then, due to the collision, it should be an elastic collision. So if this is an elastic collision, the kinetic energy before would equal the kinetic energy afterward. But we also know that this explosion should add energy. So oddly, the kinetic energy after should be greater than the initial kinetic energy. That's the important thing to notice here, is that spring is adding energy to the system. And it looks like these two carts are not stuck together going the same velocity. So let's set out to determine what's going on with the conservation of momentum. So we have the initial momentum, which is m1 v1, and afterward we have m1 v1 prime plus, we'll call this v0. And that way we'll avoid using the prime. mv0 equals m1 v1 plus m2 v2. Now the m's are all equal to each other. So in this equation then, the m's drop out. And to be a little more precise, we could say m1 v0 equals m1, factoring out an m1, v1 plus v2. And so then the m's cancel. And we're left with v0 equals v1 plus v2. And the initial velocity we know is 1. So the velocities afterward must add up to 1 for the momentum to be conserved. So these are the velocities afterward. These two add up to 1. These two add up to 1. These two add up to 1. And these two add up to 1. So based on the law of conservation of momentum, what this is saying is that any one of these possibilities could be true. Any one could be true. Now what this one says, the first one says, is that cart 1 stops. The second one says they stick together. Now the fact that they stick together, we know when there's a sticky collision that the kinetic energy is lost. So what that means is this tells us it can't be choice B, because there would be energy lost due to the collision. And this one says Choice C says the first one moves off in a positive direction and the other one moves off in the negative direction. And the same thing happens for choice D, just faster. So we're left with 3 choices. Now, so we have 3 choices that are elastic and that are elastic and the momentum is conserved. So now the second part of this is that the kinetic energy should be larger. And if we calculate the initial kinetic energy, it's 1/2 mv0 squared. So it's 1/2 m1 squared. So it's m/2 is the initial kinetic energy. And if you notice, that's the kinetic energy we have afterward because the velocity is 1. So this kinetic energy is m/2. So the initial kinetic energy is m/2, and this kinetic energy afterward is m/2. So A doesn't fit because it has the same kinetic energy that it had before. And it shouldn't be because the spring adds more energy. Now, we can test this out below and say we have 1/2 m 0.5 squared plus 1/2 m 1.5 squared. And that is m/2 times 0.25. And here we have m/2 times 2.25. So what we end up with is 2.5 m/2, which you can see is larger than m/2. Right? So 2.5 m/2 is greater than 1 m/2. And we do the last one. We have 1/2 m, velocity of 1 squared, plus 1/2 m times 2 squared. And you can see we have m/2 plus. So this is the initial. And now we have m/2 times 4. So we actually have 5 m/2. Or we have 5 times the energy we originally have. But both of these have more, and that's why it's choice C and D.